Okay. All right. So we're going to look at limacons today. What makes this equation different than the other ones that we had looked at before is that, do you guys see how there's this extra term that's in front instead? Okay. So instead of just like a cosine whatever, we have a plus b sine or cosine of theta. So notice that theta is on its own, but we have those extra terms. And so there are 4 different types of limacons. And they are differentiated by the relationship between that constant and the multiplier in front of the trig function. So one of them is if we compare a and b and it's less than 1, we end up with something called a limacon with an inner loop. Okay. Notice that it does have a point at the pole. When we've got a over b, and when we find that ratio and it's equal to 1, that's called a cardioid, which is kind of like heart-shaped. Now, I know like with a heart, we usually think about the bottom like coming down to a point. You know what I mean? Well, this one's sideways. But you know how we usually think about the heart coming down to a point? Do you guys see it doesn't come down to like a sharp point, that it's more curved like that? But that's the best the polar can do for a heart, you guys, okay? And you know how when you go to the hospital for heart stuff, you go to see a cardiologist. So that's how I remember that that's cardioid, okay? And notice the cardioid also has a point at the pole. Now, when your ratio is between 1 and 2, that's called a dimpled limacon. So it does like curve in a little bit, but you see that the dimpled limacon doesn't quite make it to the pole. That differentiates the visualization from the cardioid. And then when we have this convex limacon, that's when a over b is greater than or equal to 2. And so like this side right here, it doesn't like dimple in. I'm going to be really technical and call this, it's flat-ish, okay? So it doesn't bubble out like a circle would, but literally it's like the part over in this one, the part on the right is very round, but then the point on the left, like someone's like, is it like a vertical line? Like ish, but not quite. Like it's really close to that, but there is some curvature that exists there, okay? So again, this is what differentiates the different limacons from each other, okay? The ratio between A and B. So when we graph limacons today, we're going to identify the symmetry that exists. We're going to decide what kind of loops there are, if any. And for the loops, we're going to compare A and B, just like we looked at here, to decide what type of limacon it's going to be and what kind of loop. Okay. When we talk about finding the zeros, this is just kind of an FYI. That's not necessarily something I'd have you find in this case, because it's a 0 when it lands at the pole. So that's just kind of something maybe to take note of. If we want to find it, we can do that. We'll talk about when we do have zeros and don't have zeros. And then something called quad angles. We're going to look at where we have polar axis intercepts and theta equals pi over 2 intercepts. So when we have polar axis intercepts, that's where it intercepts what we used to think about as the x-axis. Notice that's going to happen when theta is 0 and when theta is pi. So that's going to happen when theta is 0 and theta is pi. And then the pi over 2 intercepts we're going to find when theta is pi over 2 and 3 pi over 2. Okay. Okay. We will sometimes find other convenient points just as an FYI. You guys know that I try to be a perfectionist. I don't always succeed, but I just sometimes like my graphs to look a little better than like, I don't know, a rough sketch. And then the maximum values are things that we can identify after graphing. Okay. So when we graph these, the first one we're going to graph together is r equals 4 minus 3 times the sine of theta. Now, the nice thing about the limacons, you guys, is that, you know how in the rose curves, like extra symmetry would pop up? That doesn't happen here, okay? So because of the equation, what type of symmetry will we have in number 1? You can talk to me even though we're videoing. Good. Theta equals pi over 2. So that's going to be the symmetry that we end up with here, okay? So as far as the loops, we're going to compare A and B. And so our A in this case is 4. And our B is 3. And we can see that this is between 1 and 2. And if we look back up here, it says that when our ratio of A to B is between 1 and 2, that the name of this is going to be a dimpled limacon. So you don't need to write this, but this means there's going to be a little dimple. And so then the name is going to be the dimpled limacon. Okay. And that's a little CD under the C. If you don't write the CD, that's fine. Okay. So that's called a dimpled limacon. All right. So now that we know what it should look like, let's find these different intercepts. So the polar axis intercepts, we said that we're going to find when theta is 0 and pi. So let's see what happens when theta is equal to 0. That means my r would be 4 minus 3 times the sine of 0. We won't write this out every time, but I just want to make sure you understand, you remember where we got these points from, okay? And what is the sine of 0? 0. So we have 4 minus 3 times 0, which is just r equals 4, okay? So that means we're going to have a point at 4, 0. Remember, our points in polar land are r theta. We also can find what happens at theta equals pi. And we'll just put pi in place of theta in our polar equation. 4 minus 3 times the sine of pi. And what's the sine of pi? 0. So 4 minus 3 times 0 is again 4. So then we end up with the point 4 pi as well. Now let's look at our theta equals pi over 2 intercepts. Let's see what happens when theta equals pi over 2. We're going to take r equals 4 minus 3 times the sine of pi over 2. And what is the sine of pi over 2? 1, okay? So then 4 minus 3 times 1 gives us an r value of 1. So we're going to have a point at 1 pi halves. And then we'll also find out what happens when theta equals 3 pi over 2. Again, I won't write this out every time for all of our examples. I just want us to know for our first example how we found these intercepts, okay? So we'll put in 3 pi over 2. And what's the sine of 3 pi over 2? -1. So what's my r? 7. So I have 7 3 pi over 2. Okay. And I like finding those before I start plotting, but because this one is a 7, do you guys see I might want to go by 2s for my radii that are here? So I'll start labeling these. So I'll go by 2s instead so I can fit all of my intercepts on the polar axis and on the theta equals pi over 2 axis. And so 4, 0 is going to be over here on the right. 4 pi is going to be over here on the left. 1 pi halves will be up here. Remember, we went by 2, so I'm going in the middle. And then 2, 4, 6, 7, 3 pi over 2 would be here. Okay. Now, real talk, all right? These are the points that I care most about, all right? If we were to try to connect these, okay, it might look, you know, something like this. If we try to connect it, I don't know, like, if you want to do that in your homework, that's fine. You know that Mackie likes to like aim super high, right? Okay. So what I'd like us to do, at least for this example together, is talk about how we could find some additional points to go along with that. And so I try to think of like nice values for the sine of theta. Like sine of theta is nice when it equals 1, right? That's pretty. -1 is pretty. 0 is pretty. But some of those other values on the unit circle aren't so pretty. But what's one of them that's kind of pretty? 1/2. That's nice, right? So let's think about when sine of theta is plus or minus 1/2. What family is that? Pi over 6 family, all right? So let's see what happens when theta equals pi over 6. Okay. That would give me r equals 4 minus 3. And then I'm not going to write sine of pi 6. Didn't we pick sine of pi 6 because that was going to give us something pretty like 1/2? Okay. So I have 4 minus 3 times 1/2. So that's 4 minus 1.5. So that gives me about 2.5. Well, it gives me exactly 2.5. So I'm going to have this point 2.5 pi 6. Okay. So here's pi 6, and I'm going to go 2 and a little more. Okay. Now, I'm not going to bother doing 5 pi 6 because doesn't this have symmetry with respect to theta equals pi over 2? So that means that the 5 pi 6 angle is going to be the same over here at 2.5. So now let's think when sine is -1/2. So that could be when theta is 7 pi 6. So that means that r is going to be 4 minus 3 times -1/2. So this gives me 4 plus 1/2, which is 5.5. So I'm going to have 5.5 and 7 pi 6. So at 7 pi 6, I can go 2, 4, 5.5. And I can then reflect for 11 pi 6 as well. Do you guys see that just gives me a little more accurate of a shape? Okay. Again, in your homework, I don't care. But if you were to present this at some sort of like conference, do you understand how nice those points are, how it makes it a lot nicer? Okay. So then we'll connect those points. And then that will be our dimpled limacon. Let's say that you tried to find the zeros. When you find the zeros, that's when you would set r equal to 0. So you'd have 0 equals 4 minus 3 sine theta. So you could move that over and say that 3 sine theta equals 4. So the sine of theta equals 4/3. At what angle will the sine of theta give you 4/3? It doesn't, right? What's the maximum sine can be? 1. So do you guys see that there aren't going to be any zeros? Do you also see how then there wasn't a point at the pole? Okay, so that's how the zeros kind of correspond to the graph in that regard. Okay, so again, in a test situation, I need you guys to be able to identify the symmetry, the type, and then for sure these different intercepts. Okay. Okay. All right, so then number 2, 1 minus 2 cosine theta. Okay. We can identify the symmetry right away. The symmetry here is going to be with respect to what, based on the equation? Polar axis, I hear. Good. So we have that with respect to the polar axis. And let's think about if we're going to have any loops. We're going to compare A and B. My A is 1. My B is 2. And so I can see that this is less than 1. And if we look back at our rules, when A over B is less than 1, that's a limacon with an inner loop. So this is going to have a loop, and that will be our name, limacon with an inner loop. So the type of limacon, when we want the name, don't just say limacon. Tell us what type that's going to be. Okay. All right, so just like we did in the other question, let's find our polar axis intercepts. So that's going to be when theta equals 0. And so again, instead of substituting it in, like writing cosine of 0, I'll just put what that is. So I'm going to take 1 minus 2 times the cosine of 0. What is the cosine of 0? 1. So 1 minus 2 times 1 gives me -1. So I'm going to have -1, 0 as one of the points. Okay. Then I'd also want theta equals pi. And so I would take 1 minus 2 times the cosine of pi. The cosine of pi is -1. So I'd have 1 minus 2 times -1, which would give 3. So then 3 pi is going to be another point. As far as the theta equals pi over 2 intercepts, we can see what happens when theta equals pi over 2. So that means I'm going to have r equals 1 minus 2 times the cosine of pi over 2. And what's the cosine of pi over 2? 0. So that's just going to be r equals 1. And then we could do the same for 3 pi over 2. R would equal 1 minus 2 times the cosine of 3 pi over 2. The cosine of 3 pi over 2 is 0. So then we have a point at 1, 3 pi over 2 as well. Okay. So if we want to plot these points, my r doesn't look that big, all right? So I can just keep that the scale 1, 2, 3, 4. -1, 0 is going to end up over here on the left, isn't it? Because I need to go backwards from 0. So the theta equals 0 is this way, so that means -1, I have to go backwards. 3 pi is also going to be over here on the left. And then I'm going to have 1 pi over 2 and 1 3 pi over 2. Okay. Again, not very helpful, right? Okay. So the one thing that we didn't have is a point at the pole in the other question. What we could do is we could see if this would have a point at the pole, if this has a 0 to it. So we can say 0 equals 1 minus 2 cosine theta. So that means that 2 cosine theta equals 1. So that means that cosine of theta equals 1/2. Is there a theta value that would give us 1/2? There is. What's that theta value for cosine? Pi over 3. So that means that there's going to be a 0 at 0 pi over 3. The thing is that it doesn't necessarily matter what that theta is. It just matters that there is a 0, which means that we are going to have a point at the pole. Okay. And the way that you make the loop, and I'll show you with the additional point as well, but we start here on in that little inside part, and we like go down and around and pass through this guy, and then we go down, we pass through this guy, back through the pole, and then we end up here. I'll do it in a different color as well, with some other points, but that's kind of the gist of that. We used 1/2 in the last example. We see that 1/2 in this case gives us 0. So what we could do to get additional points is we could use -1/2. And so if we wanted to see when cosine was -1/2, that's going to be when theta equals 2 pi thirds, sorry. When theta equals 2 pi thirds. So then we could say, all right, r equals 1 minus 2 times the cosine of 2 pi thirds, which is -1/2. And so that means that my r value would be 2, sorry. -2 times -1/2 is 1, so 1 plus 1 gives me 2. So that means I'm going to have a point at 2 pi thirds. So 2 pi thirds is here, 1, 2. And then we know that there's symmetry with respect to the polar axis. So that means that I could have a point down here as well. Okay. So this one doesn't flesh out quite as nicely because of the zeros, but let me trace this one more time for you, okay? So we start kind of on the inside, and we go down to the pole, and then it's like you go around in a circle, okay? Then you go through the pole again, and then back to that inside loop, okay? If you were to graph on the graphing calculator, especially if you have an older one, you'll see it really quickly like trace out that way, okay? But that's kind of what happens as theta increases. That's the shape that we end up getting, okay? Again, I don't need the extra points in a test situation. I just need you to make it look like a limacon inner loop. But I just like it better with a little more definition. All right. Okay. So let's try another one together, and then I'll let you guys do one on your own. So this one, number 3, we have r equals 2 times the quantity 1 plus cosine theta. Let's make this look more like the form that we're used to. So we'll maybe say this is 2 plus 2 cosine theta. And based on the equation, you guys, what kind of symmetry would we have? Polar axis, because we're dealing with cosine. Good. Okay. Now, as far as the loops go, we're going to compare A and B. A is 2. B is 2. So that gives me 1. And when we look at our rule, when the ratio of A to B is 1, that's where we have a heart shape that's not pointy, okay? And so again, the official name for that is the cardioid. Okay. So 2 I's in that one. Cardi, and then oid. All right, so let's find our polar axis intercepts. So this is going to be when theta equals 0. So that means r is 2 plus 2 times the cosine of 0. The cosine of 0 is 1. So that gives me 2 plus 2, which is going to be 4. So we're going to have a point at 4, 0. And then we'll see what happens when theta equals pi. When we have theta equals pi, what is the cosine of pi? -1. So I have 2 plus 2 times -1. So what does that give me there? 0. So then I have 0 pi as another point. For the theta equals pi over 2 intercepts, if I put in theta equals pi over 2, r is going to be 2 plus 2 times the cosine of pi over 2, which is 0. So I'm going to have the point 2 pi over 2. And once you get used to this, this thing, do you guys see that there's always going to be one pair of intercepts that have that symmetry to it? If you see that this is going to also be 2, 3 pi over 2, since there wasn't symmetry here, that's fine. Or you can substitute it in. Substitute in that 3 pi over 2. The cosine of 3 pi over 2 is 0. So again, we get 2 plus 2 times 0, which is just 2. So those would be our points. We have 4, 0, and looking at the r values, I can just keep it that normal scale. So I have 4, 0, 0 pi, which ends up landing where? At the pole. And then I have 2 pi over 2 and 2, 3 pi over 2. Okay. Again, if you want just to connect, that's fine, except when people connect, a lot of times I get a heart with a point on the end, all right? That's not the way these polar graphs are, okay? It's not pointy at the end. We like to annoy you in different ways, all right? So if you're going to make it from here, make sure that it still is kind of, you know, that round shape here, and then you can go in and meet at the pole. Okay, just try to make it symmetric. That's one of my other issues. I cannot draw to save my life. So that's why I think it's a nice idea to put in those additional points. So another thing I could think about is when the cosine of theta is plus or minus a half. So again, that's going to be the pi thirds family. So if I have theta equals pi thirds, then my r is going to be 2 plus 2 times the cosine of pi thirds, which is 1/2, so that's 3. So I get a point at 3 pi thirds. And then I can use that symmetry as well to go on the other side. So instead, so down here, I can do basically 5 pi thirds. So 3 5 pi thirds as well. And then if you wanted to know, we could use theta equals 2 pi thirds. And then that would give me negative 1/2. So that would be 2 plus -1, which is going to be 1. So we'd have 1 and 2 pi thirds. And then again, for people that like are anxious like me, I feel better about this. This gives me a lot nicer idea of what that cardioid is going to look like. Okay. Okay. And again, just on the end there, it's going to be curved. Okay. If we were to find the 0 like we had before, do you guys see that we already found where the 0 was at this point here? But if we did find it, we could do it in that way as well. So you could say 0 equals 2 plus 2 cosine theta. So you'd want to know when cosine of theta equals -1. Isn't that when it's pi? And theta is pi. And so then that would give us 0 pi, which we had already gotten here. Okay, but if you wanted to find the 0 or just to verify your work, you can do it that way, right? You guys ready to try one on your own? Really excited. All right, you guys, try number 4, all right? And I'll come around and work on that with you guys, okay? Okay, so we've done number 4. Maybe we're still working, that's okay. I don't know why I rewrote the equation. But our symmetry, because we're dealing with sine, is going to be about theta equals, with respect to theta equals pi over 2. Once again, the ratio of A to B was 1, which means that we're going to have a cardioid. The polar axis intercepts end up being 3, 0, and 3 pi. And then the theta equals pi over 2 intercepts end up being 0, pi over 2, and 6, 3 pi over 2. You just need to make something that is symmetric, that does touch the pole, okay? Again, it will touch the pole because it is a cardioid. The cardioid touches the pole. The limacon with an inner loop touches the pole. The dimpled or convex won't. And then, of course, you know me, I found my extra points. So again, I'm just going to use when sine is plus or minus 1/2. So I'm going to use things in the pi 6th family. Pi 6 I reflected to help me find the 5 pi 6. And then 7 pi 6 I reflected to help me find the 11 pi 6. Okay. And then I'll leave that up while we look at number 5. It says, give an example of an equation that would give a convex limacon with symmetry with respect to the polar axis. What does the idea of a convex limacon tell you about the ratio of A to B? If we look back, what does that ratio of A to B have to be? Greater than or equal to 2. And because it's with respect to the polar axis, what does that tell us about the equation? That it has to deal with cosine of theta, okay? So write an equation. And then let's have 3 people give me an example of what they have when you're confident. Okay. Who wants to give me an equation? Yes. Good. 6 plus 2 cosine theta. I love it. Okay. Any others? Anyone else willing to share? G, thanks. Okay. R equals 5 minus 2 cosine theta. Honey? Okay. Now, we understand all y'all had 2. It's okay if this number isn't 2. You get that, right? It's just that the ratio of A to B has to be greater than or equal to 2. Okay, and that's a little bit about limacons.